united we stand. But at Division, we ball.
Hey y'all, welcome back. Today we are going to talk about Euclidean division and prove Euclid's division lemma. Euclidean division and algorithms to compute it are fundamental for many questions concerning integers, such as the Euclidean algorithm for finding the greatest common divisor of two integers. The operation consisting of computing only the remainder is called the modulo operation and is used often in both mathematics and computer science. Euclid's division lemma, also known as the Division Theorem, states that given non-negative integers greater than 0 and b, there exists an integer q greater than or equal to 0 and an integer r, which is in between 0 inclusive and a exclusive, such that b equals a times q plus r. To clarify, a is the divisor, b is the dividend, q is the quotient, and r is the remainder. We want to show that if you divide b by a, there must be a q and r with the aforementioned conditions that satisfy the equation b equals a times q plus r. The computation of the quotient and the remainder from the dividend and the divisor is called Euclidean division and is what most people mean when they just say division. One last thing before we start the proof. You should know that the division theorem or Euclid's division lemma, or whatever you want to call it, is often referred to as the division algorithm because the proof lends itself to a simple division algorithm for computing q and r. So anyway, let's begin. Let S be the set of b minus a times x such that x is a non-negative integer and b minus a times x is greater than or equal to 0. Then S is a set of non-negative integers and is non-empty because b equals b minus a times 0 is in the set S. Using the well-ordering principle, we can say S must have a least element, r. Clearly, r equals b minus a times q for some integer q where q is greater than or equal to 0. Next, let's show that r is in between 0, inclusive, and a, exclusive. Since r is in S, r is greater than or equal to 0. R minus a must be in S because if it wasn't, then r minus a would be greater than or equal to 0, and r minus a equals b minus q times a minus a, which equals b minus 1 more than q times a, which would be, you guessed it, greater than or equal to 0. So yeah, r minus a is in S. This contradicts our assumption that r was the least element of the set S. Thus, r is less than a, and so b equals q times a plus r, with r being in between 0 inclusive and a exclusive. QED. Thanks for watching, and I'll see you next time. Oh, and if you're some joker that needs the details of the well-ordering principle laid out, basically it states that any non-empty set of natural numbers has a least element. But let me really break it down. Let S be a set of natural numbers with no least element. Let P of n be the statement no number less than or equal to n is in S. Observe that if m is in S, then P of m is false. So by showing P of n is true for all n, we will show that S is empty, which is what we want to show in our proof. Now it's pretty obvious that P of 1 is true. Duh, if it wasn't 1 would be in S, and since all natural numbers are greater than or equal to 1, S would definitely have a least element. So say that P of j is true for some j greater than or equal to 1. If P of 1 more than j is false, then some number less than or equal to 1 more than j would be in S. But P of j is true, so there can't be a number less than or equal to j that can be in S. But hold on. If that's the case, then j plus 1, the only number less than or equal to 1 more than j, which is not less than or equal to j, would be in S and would be the least element of S. Simply impossible. Thus, if P of j is true, then P of 1 more than j is true. By induction, P of n is true for all n, and S is a sad empty set. Now we can say that any non-empty set of natural numbers has a least element, QED. Still want more? Okay, I've got one left in me for today. Let's prove that the Q and R from earlier are unique. Suppose that B was equal to both A times Q plus R and A times S plus T. We want to show that Q must equal S and R must equal T. Let R be greater than or equal to T. Then subtracting B from itself gives us this statement. But wait, 0 is less than or equal to R minus T, which is less than or equal to R, which is less than A. So if we divide by A, we would get this compound inequality. This implies that 0 is less than or equal to S minus Q, which is equal to R minus T divided by A, which is less than 1. Since S minus Q is an integer, we must have S minus Q equals 0, so Q equals S and T equals R. We've now shown that the quotient and remainder are unique. QED. Hope to see you soon.